Okay, so here we're going to take a look at the alternating series. So up to now, all of our series tests have focused on non-negative terms, all right? In other words, positive terms, all right, or zero. Okay, so here we're going to take a look at an alternating series. Now, what is an alternating series? The feature that describes an alternate series, an alternate series is this -1 to the n+1 or the n power, right? What this does, as you can see from what's listed here, it really just changes from positive to negative as our counter of n increases, right? So that is the point of that -1, right? And that's what makes it alternating, right? This b sub n, these are non-negative, right? They're positive. They're non-negative, they're greater than 0. Okay, and the -1 flips it from positive to negative. Now, all the tests that we've done up to this point do not apply to an alternating series test. So we need new tests. The good thing is that there is only one test, right? And it's a very straightforward one. It involves taking a limit. But how we interpret that, there are some subtleties in the alternate series test. All right, so here, the idea here for the alternate series test is this. All right, so the alternating series test, so we given an alternate series test in the form of -1 n+1 or -1 to the n, right? All the difference between those two quantities here is that when n is 1, it starts off, when n+1 is the power, it starts off positive, right? Because n is 1, so we start off with squared and even number. And when it's just n, then it just starts off being negative. That's all that tells me. So an alternate series in that form, right, converges if b sub n+1 is less than b sub n for all n greater than or equal to 1. And, right, so both of these conditions must hold. The limit as n goes to infinity of b sub n is 0. This is known as the alternating series test. All right, now a couple things to notice here, right? If both of these, or neither of these conditions are met, or one of them is met but the other one is not met, that does not tell me anything about the alternating series. Okay, so just keep that in mind, right? It doesn't tell me divergence, right? So this is strictly a test for convergence. All right, and all that means is that's the only thing we can gain, only kind of knowledge that we can gain from this, right? Either we can apply it and it converges, right? Or just the test does not apply. Okay, and we'll talk about instances if it doesn't apply. What are some other things that we can do? Okay, so just keep that in mind, right? And the idea for this alternating series test here and why it works, right? If we think of, right, the sums here, b sub n, right? So b sub n is greater than 0, and it's also, right, decreasing. Strictly less than, bigger than 0, right? Yes, less than or equal to b sub n. Okay, so the idea here is that, right, what happens if we think of the partial sums, right? So the first partial sum is just some Okay, sorry about that here. So the idea here is, so we're given 1 n+1 b sub n, right, and 0. This inequality holds, right? And also the limit as n goes to infinity of b sub n is going towards 0. Okay, so those two hold, right? Now, why does this alternating series theorem work? Well, if we think of the partial sums, right? The first partial sum is just the first term. So it goes to some value here, right? We'll call that S1. Right, well, when I add B2, right, it's alternating, so the next one is negative, but also less than whatever the value of the previous term is. So the second partial sum, right, it cancels out some of it, but not necessarily all of it, right? Maybe, right, because this inequality does hold, but we'll just say here, for our purposes, that it doesn't, right? But it does go towards 0 again, right? And then the same thing goes, well, now for the third partial sum will just be the third term in this case. So this is our B1, which is positive, and this is negative B2. Remember, these B sub n's themselves, those are positive, right? So the only sign changes comes from our alternating part, right? And now our B3 here, B3 goes somewhere here, right? Again, maybe all the way, but not necessarily. Right, and then the next one, negative B4, right, it goes in the other direction, not necessarily all the way, so we get S4, S3, and we keep playing this game where we just kind of keep going back and forth till at some point it settles on some sum. So that's kind of this idea for the alternating series test and why it is these two conditions are enough to prove convergence, right? And that's all that proves, right? Our convergence. So let's take a look at an example here. All right, so here we have okay. So we have here the alternate harmonic series, right? We're familiar with the harmonic series itself, this one, which we've shown in a couple of different ways that it is a divergent series. But that does not apply here because this is a different type of series, in an alternating series. So what we look at here is, well, here we look at here, so first of all, we confirm that it is decreasing. So the next term is in fact less than or equal to the previous term. And that is true. Right? Remember, when we add something to the denominator, right, it is making it, the denominator is making it bigger, but the overall fraction is getting smaller. So this works. And also the limit as n goes to infinity. Now remember, when we take these limits, it's of the non-alternating part, right? We kind of ignore that -1 to the n plus 1 is n minus 1, whatever that happens to be, right? Well, in this case, this is 0, right? Because n just grows infinitely large in the denominator. So both of these are met here, okay? So both conditions are met, right? So that is enough to show that the alternating harmonic series, this one is, in fact, a converging sequence. All right, so that's interesting, right? Here, its corresponding non-alternating one is divergent, but this alternating one is a convergent sequence. Okay, all right. So now here, let's take a look at this. That's 3n, not 3 to the n. All right. Now right away when I see this, I look at the limit again of the non-alternating part. Right, and we see as n goes to infinity, these are the same power, so that equals 3/4. So it is not 1, or excuse me, not 1. It is not 0, right? So here what we have is that this is not, the alternating series test does not apply. Okay, again, it does not show divergence, right? So it's a very subtle thing that we should keep in mind here, right? This alternating series says if these two conditions hold, then it is convergent. But it does not say anything else, right? That's all it says, right? So be careful, right? So the alternating series test, our AST, does not apply. Now, in general, if we take a look at this, yeah, 3n over 4n minus 1, right? The limit of this is really, well, actually, it doesn't exist, right? If we think of the limit here, this value is going to 3/4, right? But the -1 is going from positive to negative, right? So what's happening here is that the limit actually does not exist, right? And therefore, our series diverges, right? But in this case, it diverges because of the divergence test. Okay, so just keep that in mind here as you work through the alternating series test. If those two conditions hold, then it is telling me it converges. If either of those ones fail, then it does not apply, right? It does not telling me, it does not say anything about its convergence, or excuse me, it does not say anything about whether it diverges or not. Okay, or its convergence.